Hey everybody, welcome. This is Obi-Wan Pez for N-Simplex Pachinko. It's totally not what I wanted. Or something. Alright, there we go. Like I said, this is Obi-Wan Pez for N-Simplex Pachinko, and welcome this evening. Hey Lana, how's it going? So we've got, I have, nothing particularly lined up, but definitely we can talk about all sorts of cool stuff. So I think tonight, just to start, I'll do a bit on implicit differentiation. Mates, welcome. It's probably still wrong. Alright, so there was somebody asking about implicit differentiation a while back, and they wanted to ask about, like, what exactly do I do? Because I've got, sorry about that. I've got all of these variables that are kicking around everywhere, and so if we come up with an equation like 2x squared y plus 3y cubed x minus 7x plus y equals 4, let's just say. So they would like to know, for instance, what kind of slopes are there going to be at various moments in time or various locations in this larger picture. So, that's interesting. I don't see my cursor anywhere. Huh. Okay. Anyway, that thing right there. Yep, so, right there. So, for instance, one of the points that might be on this, you can find a particular point that is on this curve. So I am going to kick up Desmos here and turn it back to display capture. All right, so if we do something like, 2x squared y plus 3, I guess I could trade this around, but whatever. 3y cubed x minus 7x plus y equals a, just some value that we pick. And for this particular value, we're going to use 4. So if we see there can be all sorts of, that's a perfect one to pick. So there can be all sorts of values that we pick. Usually in a calculus class, you'd find a nice one like this 0.4. Yeah, that's just perfect. So, oh, right. done this particular problem in a while. I forget the exact phrasing that they would probably use, and my calculus book is currently holding up my other monitor. So, I mean, you could say goes through 0, 4, but at the same time it's a tangent line, so it's kind of like, but yeah, that's fine. So what is the slope of the tangent line that's going to go through the point 0, 4? Matt, has any particular interest? Anyway, we want to know what the slope of the tangent line is that goes through the point 0, 4. As we saw on Desmos, this was more or less, this function was more or less kind of going like that, and then swinging down to the x-axis. We had the y-axis that went sort of somewhere up here-ish. So we want to know what the slope of this tangent line is. It should be pretty large. I don't think it's vertical, but should be a large number. So to get the slope of the tangent line, what we need to find is dy dx. And the way to find dy dx is to go about and take the derivative of this entire function here. And then, I shouldn't say function, it's not actually a function like y of x or x of y or anything like that. It's kind of it could be a parameterized function, so it could be a function on time or something like that, but you don't have any particular variables that are given, x and y, over which this is a function, technically. All right, so what we can do here is take the derivative of the entire thing. Now, you have definitely been taught to do it like this. You take d dx, which is the derivative with respect to x of 2x squared y plus 3y cubed x minus 7x plus y equals 4. Technically, we're doing d dx on the other side as well. All right, so that causes the right-hand side to become 0. Let's not kid ourselves. We're going to need a lot more room. So over here, again, most of the time you're doing this where you're saying, okay, take the derivative of the first term. Since these are all added and subtracted, we can separate them out and take their individual derivatives, which means that we're taking the derivative of 2x squared y. It's going to be 2 because 2 is a constant, multiplied by the derivative of, here we have a product rule between x squared and y. So, product rule, you say x squared, we take the derivative, it's going to be 2x. And then we have y, which remains. Then no, that's fine. You're right. The 2 drop down because of the power rule. Here we go. Okay. Then we get plus. This 2 is already here. We get x squared times the derivative of y with respect to x. So this is dy dx. Okay. Then the next one, we get a plus. We take the derivative of 3y cubed x. I don't know why this is self-sabotage, really. It's picking the same number for the coefficient as is going to come down from the power rule. That's sabotage. So here we say that this is going to be 3 times the quantity. This is yet another power rule between y cubed and x. So we're taking the derivative of y cubed. This is going to be 3y squared. And then by the chain rule, you have to take the derivative of the inside, which is y. So dy dx times the x that was already there, plus y cubed times the derivative of x is going to be 1. So dx dx. Just going to be 1. I left off the, no, that's fine. We didn't have a 1 earlier. I was thinking we might have. But then we have here a negative 7. And again, dx is going to be 1. So negative 7 times 1. Plus derivative of y is going to be dy dx. And again, that's equal to 0. We already had that. Swap sides. All right, for this, then we're just going to do simple algebra here, where we're going to multiply in the 2. So this becomes 4xy plus 2x squared dy dx plus 3 times 3 is 9 y squared dy dx times x. Okay, we'll move that. All right, and then we get a y cubed times 3 minus 7 plus dy dx. All right, we want to get all of the dy dx terms together. And they're all here. They're all positive at the moment, so I feel like keeping them on this side. And we'll shift everything else over. So subtract off a 4xy. That's a dx dy term. This is going to be a minus 3y cubed and a plus 7 to get rid of all of these things. So 4xy minus 3y cubed plus 7 is going to be equal to, on this side we have left a dy dx multiplied by, here we have 2x squared plus 9. I'm going to switch this around finally. So 9xy squared. Just to stay consistent, I almost always do x first, y second. It's just habit, really. All right, and plus 1. Which means that dy dx is going to be equal to negative 4xy minus 3y cubed plus 7 divided by 2x squared plus 9xy squared plus 1. And at this point, we really can't do a whole lot with this. Yep. So at this particular point, again, 0, 4, we want to plug all of that in, 0, 4, and get all of the appropriate dy dx value out of this. So dy dx is equal to, here we have 4 times 0 is going to be a 0, minus 3 times y is 4, and that's going to get cubed, plus 7 divided by 0 plus 0 plus 1. Yep, big number. Negative direction, but still big. All right, that is going to be then 4 cubed is going to be 64. 64 times 3 is 192 in the negative direction. Plus 7 is going to get us a negative 185. This is over 1. So dy dx at 0, 4 is going to be negative 185. If you wanted to find a line which went through that particular point, it's nice and easy. It's going to be negative 185x plus 4. Right? We already know that because this is the y-intercept. It makes it nice and easy. If your point is not on the y-axis, then I would suggest doing point-slope form. So again, point-slope form is you're just taking the slope equation say m is equal to y minus y1 divided by x minus x1. Multiply your x's over, and you end up with y minus y1 equals m times x minus x1, or y equals m times x minus x1 plus y1. So any of those you can start there and then work through. Now, I was talking with Soul Reaver and probably Kiwi Gamer Romania a few weeks ago about how to change this up just a little bit. It doesn't really change a whole lot, but it does change how you might look at this when you come out with how to do derivatives later, especially when you're talking about in Calculus 3 doing vector calculus. So you want to know whether your derivatives that you're taking are going to be ordinary or partial, because that's going to make a big difference. So if you do this, where you have, again, 2x squared y plus 3y, I'm going to just switch that around, xy cubed minus 7x plus y equals 4. If I want to take the derivative of this, and let's say I just want to be kind of there is, in fact, a Discord that I am a part of. I'm not sure if I'm supposed to be giving it out. It just goes by the name of Homework Help. Yeah. Goes by the name of Homework Help. But like YouTubers, I'd say probably Patrick JMT, Khan Academy, and Purple Math, I think, are kind of the three that like cover practically everything. I have done a bunch of stuff with trigonometry, but I don't know that I've done anything with specifically inscribed angles. So I'm guessing inscribed angles into a circle. Sazawi? So what I had suggested people start thinking about is, what if I just want to take like a derivative and be very general about it, and maybe make a yeah, no problem. And maybe make a, and if you have a question, you can drop one here, and I'll cover that next if you want. It'll probably be 5-10 minutes. So with this, I can drop a general derivative on this, and then later I can decide if it's going to be an ordinary or a partial derivative, and then depending on what the answer, what kind of derivative you want, it's going to change your answer, but you know, it's easy enough to fix. So if I just want a general derivative of all this, I can use the differential operator d on 2x squared y plus 3xy cubed minus 7x plus y, and then use the general derivative operator on the other side as well. Again, the derivative of this thing is 0, so it doesn't matter whether it's partial or ordinary, right? D of 4 is going to be 0 no matter what. Am I here? No, I'm off. Okay. So if D of 4 is going to be 0, and then on this side, you can start looking at this and saying, all right, let's take the derivative of 2x squared y regardless of anything else. This is probably going to take more room than I actually have, but it's fine. So here we have the 2, which comes out front still. Then we take the derivative of x squared y. Actually, it won't be too bad this time. Then we take 3 times the derivative of xy cubed minus 7 times the derivative of x plus the derivative of y. Perfect. So then from here, we look at this and say, this is a power rule. We've got now 2 times the quantity. Take the derivative of x squared, and we multiply by y. This is, again, just mostly for like, if this is your first time going through this process, you probably want to take it nice and slow and go easy with it. Some of the other times that, or once you get used to it, it just becomes second nature. You do it the same as you do any other derivatives. You just kind of run through it real quick. So we do d of x squared times y plus x squared times d of y, right? Just regular power rule. And there ends the parentheses for the 2. Plus 3 times, here we have the derivative of x, times y cubed, plus x times the derivative of y cubed. Again, power rule. Okay, minus 7 times the derivative of x, we'll come back to that later, plus the derivative of y, again, equals 0. And then again, we're going to look at all this stuff. So 2 times, let's just keep it in parentheses here. The derivative of x squared is going to be twice the derivative of x. Oh, no. Okay, sorry. 2x times the derivative of x. That matters. That's really important. Don't screw that up. All right, plus we got x squared times the derivative of y. Plus 3 times the derivative of x times y cubed plus x times, here we have 3y squared times the derivative of y. Just barely ended that. Okay. Okay, minus 7 times the derivative of x plus the derivative of y. Yep. So if you use the differential operator, instead of doing a specific derivative, then you can just do it very generally and treat all of your variables as if they're variables. And it's very, we can call it agnostic in terms of what you need or what you're trying to do, especially since later you can decide what you want to do with it. So do I want to take the derivative with respect to x? Then I can just go through and change all the derivatives with respect to x. And same with y. I could do, right, I can make this dx dy if I felt like it, instead of making all these dy dx. Anyway, so then multiply all this through. You end up with 4x times derivative of x plus 2x squared times the derivative of y plus 3y cubed times the derivative of x plus, this is going to be 9 xy squared times the derivative of y minus 7 times the derivative of x plus the derivative of y. Okay, now this is, again, the generalized derivative. And then if I want to do ordinary on x, then that means that the derivative of x with respect to x is going to be dx dx, or 1. And d of y is going to be dy dx, which is, again, our slope. Yeah, it might frighten off a few students if you do this for everybody, but, you know, if you do it for the students who are more calculus oriented, when they're in calculus, they might be like, oh, well, That's very interesting, especially if they've already had calculus and didn't maybe quite get it, but really want to understand it. Yeah. I've had a lot of students who have been in Calc 1 in high school, and then they were like, I didn't really get anything. Just because, their teachers are under a lot of stress. They got to get numbers and produce all this stuff. And they're not necessarily teaching them everything like behind the scenes because they just don't have time. All right, so if I then want to do partial, with respect to y, then here, everywhere that we have a d of x, this is partial with respect to y of x, which is 0. Because x is treated as a constant in terms of y. And then dy is going to be dy of y, partial, is 1. It just makes things a whole lot easier in general. Yeah, so those all have specialized functions. Um, a lot of them are transformations. So in the case of, for instance, the like you're saying, Riemann and Lebesgue, yeah. What am I thinking? The thing, I've got a paper for it right here. Of course, it's not actually right here. Chapter 8. Nope, chapter 5. It's only been like a year since I taught this. I should know this better. No, it isn't chapter 5. Okay, cool. Laplace. There we go. So, like Laplace transform and stuff like that, they all have specialized uses in order to do something in particular, in order to simplify various problems. So, derivatives in general don't really, because you've only got kind of two flavors. They come in ordinary and partial, and then you can choose what variable you want to take it with respect to, but that's generally it. Now, there are some very specific uses for derivatives, which have like a derivation, which can be useful for something in particular, but there isn't necessarily like one thing, like a different type of derivative or a different formulation of a derivative, at least most of the time. I have my Krasik book back here. My spouse and I cleaned up the office last week. Not particularly. So there are like a lot of individual uses, like I said, but not necessarily like different shapes of derivatives. Differentiation. Analytic and complex functions. So, we could probably do. Not literally we in this area because I'm not I'm not read up on it anymore. But doing things on complex functions or taking trying to transform functions into complex functions in order to take their integrals is kind of the backbone of complex analysis, which is a wonderful class if you ever get the chance to take it. Oh man, it has been a long time since I looked through this book. I mean, like, really. Or tried to look for something in particular. Yeah. Oh, there's also like partial differential equations, which end up. I mean, if you're thinking about generally just differential equations as a whole, um, like there's a lot of that going on too, where you have the heat equation, let's say, and you start there, and then try to work backward toward a solution. In terms of differential equations, ordinary differential equations, generally speaking, you've got most of the time solutions. Um, and then when you look at partial differential equations, a lot of times you don't have solutions. You have kinds of like rough families of functions which sort of approximate what you're looking for, and so you can use them and then manipulate them some to get something that resembles an answer. But a lot of times in partial, you're doing a lot of estimation and trying to do numerical methods. Yeah, most of the stuff I'm pulling up is either differential equations or or like some sort of formulation of an integral to come up with something. Oh, there is also doing things like the Jacobian. It's part of differential equations technically, but when you're looking at a nonlinear differential equation or a like slope field, you can sometimes approximate. Sometimes you can approximate um, a nonlinear differential equation as locally linear differential equations around singular points. So those are really cool. Um, if you had something that was like, I don't know if I even want to draw something because it's going to look terrible, but sure, why not? Um, you got some coordinate plane. Around this point here, there is a spiral that's going outward from here. That's terrible. But you've got another singular point, let's say at the origin, which is a saddle point. So you'll have lines that will be essentially vertical, and then as we start getting lower and lower, they'll start kicking out further and further and faster until they get out to close to our asymptote, at which point they become more or less horizontal. Right, and then on this side they would also do the same, so they'd be going this way. So that goes that way, that goes that way, that goes that way. So as you get close to these asymptotes, this kind of starts approaching these values, and then like I don't know, another singular point out here, which is a let's go with sync. So all the points star sync essentially goes like this. All points around it will eventually just move toward it directly. So the interaction between these three singular points is actually a super interesting and very difficult thing to calculate. Because again, here, all these points want to start going down, essentially, to join up with these other points here. So we want, or they want, essentially to do something like this. But if this is a sync, then there's the possibility that this is not going to, once it leaves this area, it's not going to be able to go over to here. It's going to have a pull from these lines, which is essentially going to make it do something like this. This would come up this way, and get close to this one, and then essentially go straight into it here. So along somewhere in this line, it would go something like this. If we go up a little bit further, this could like drop toward it a bit and then get pulled back away. Yeah, it can be complicated. Lines over here start going like this. And lines that are much further this way would start getting perturbed by this thing. And somewhere around here, if I've got this right, that it's spinning that way, that would actually like catch this thing and cause it to maybe curl back on itself and go then out and around. And then probably again get picked up by the other side over here. So nonlinear differential equations and partial differential equations are the majority of differential equations out there, which usually happen to describe some sort of phenomenon, whatever it might be. So like the airflow around a room is a good example of a partial differential equation that is usually extremely hard to calculate. And so if you want to like turn a fan on somewhere, and then you've got to calculate for like all of the walls, and eventually you can actually work out like furniture and stuff like that too. But most of the time you're just like, okay, here's the room if it were empty, and then let's turn a fan on up here. What would be the flow of the air around this room? Roughly speaking. You're not going to get it 100%, but you can get it pretty decently. Yeah, so what you do for these is you approximate locally. And you say like around 6, 6, we're going to take what's called the Jacobian Matrix. Yeah, that works. And you take the function that we have. So typically you've got something that's written x of t and y of t. No. Okay, you've got something that's like f of xy and g of xy. And they are a coupled system. So a system of differential equations. And basically what you do is you take the partial derivative with respect to x on f, y on f, g, x on g, and y on g. I may have this backwards, so you know. So you calculate this thing, you evaluate all of these things at this point, xy, which in this case is 6, 6, for this point only. Then when you get that done, you've got to do it again for 0, 0. And when you get that done, you got to do it again for like 3, negative 2, or whatever this is. So you got to do it for every singular point that you have, and then you find the behavior around this local system. And you look at it and you say, ah, this is what it looks like. You can kind of get a basic sense of what's going on. So it's probably one of my favorite. It's weird to say this, but it's probably one of my favorite subjects at the end of differential equations, because you've been doing like this series work, you've been doing like all these really weird like numerical analyses on stuff that's not going to work. It's never going to work. You will never get anything nice. And then suddenly you pop this in and pop out the Jacobian matrix for all of the singular points that you find for a particular nonlinear system, and it looks so nice and calm. Let's see. Yeah, it can really approximate very well. And you have, it's not 100%, but it does decently well. And within its local system, you say, oh, well, if I found that this one is I'm waving my pen around as if you can see it. So if you can approximate this as a spiral source, so it's going to spiral outward just by itself, then you also find that 0, 0 is a saddle point, and you know it's going this way. Then you can also figure out maybe what are the interactions between these things. So you might be able to find out, where's the point at which these behaviors change? Because if this wants to spiral out, right, then it joins up with this or something like that. There's got to be some point right around here where this going this way and this going this way have some sort of behavior. Yeah. It gets a little weird and difficult sometimes, but again, it was just one of my favorite things to study when we were talking about the very end of differential equations. And that's the other thing, is that this is an undergrad course, right? Like it's a second year. It's a second year course. If you're doing partial differential equations, or like the high level nonlinear differential equations, that's all master stuff. And that was what I took for my sequential classes. So we had to take a sequence of 2, and we also had to take a certain number of 100 and certain number of 200 level master's classes. And so, yeah, partial and nonlinear differential equations were my 2 main ones. And what else did I take? I don't remember what I did at 200 level. I remember the 100 level stuff was fun, because it was a lot of random things of stuff you should know: combinatorics, matrix theory. Oh, data mining was a 200 level course. That was rough. I took the data mining class as my last class, and I ended up using a lot of. I also did neural networks. I used my neural networks work to start doing some of the data mining stuff, and the instructor was suitably impressed. It didn't actually work, but I still managed to think an A in the class. Maybe a B. It's been so long. Anybody have anything they want to talk about? So mine was an applied math major. So I also did real and complex analysis. So real was a 100 and complex was a 2. That's what I took for my 2. Um, but apart from that, I'm not sure because they didn't do like numerical analysis or number theory or any of those courses because that's all like real math. Um, that's all theoretical. So ours was a very applied program. Um, it was taught by professionals um, at the I don't want to give too much away, but so there's a local college which has a tech lab which is nearby, and they run. I mean, they have people who are there to just do research all day, right? It's not academic. It's not actually affiliated with the university necessarily, apart from having its name on it. Um, but if you work there, you're not necessarily working with students. You're working like behind a carded gate, so you can have security clearances and stuff that you need to get in. I've been in a few times on field trips. It's always very interesting. Um, so they had, yeah, I know. I just like to make fun of applied math because it's my field. Uh, and I've been getting into more theoretical stuff just for fun. But I never had to take analysis, and I'm kind of a little I'm kind of a little upset about that sometimes. That like, oh, I never ended up taking numerical analysis or number theory that might have helped me at some point. And like I've been reading books on it, but it's not quite the same. And I'm older. It's a lot harder. Uh, but yeah, yeah. So the program that's there was taught by professionals who work at the lab, and so it's kind of like they're not teachers. So I being a math education major and having had multiple years of experience in teaching when I got there, I was just kind of like, oh, I would teach this so much differently. And it was a very interesting learning experience. And my spouse was also like, yeah, I wouldn't teach like that either, and I'm not a teacher. But, it wasn't awful. It was just kind of like, this is not how I would be doing this. So number theory comprises probably the majority of all the stuff that I have ever done any research in, because number theory as a whole is very accessible. So I also really like number theory for its accessibility to younger students. Oh yeah, there was one guy. I had him for 2 classes. It was amazing. He stood at the front of the room and he lectured from the book. And I was like, I did not have to pay, $1,800, $2,100, whatever, to take this class to do this. I could have done this at home. Yup, he read the book. I was like, oh. That's like the first thing they teach you as a teacher is don't do that. Come up with your own material, come up with your own stuff. And it just takes experience to really understand how it works. But at the same time, like, your notes have to evolve. You cannot be teaching the same stuff for 20 years. It does not work. You cannot do that. The students change. Even if you don't, the students change. And so you just need a new approach. So I personally try to figure out as many different approaches as possible in order to get, you know, in order to become accessible to as many students as possible. I really need to focus in and try to. Yeah, that's the other thing, is that if you don't know the material well, which I'm kind of afraid this semester because I'm teaching a class that I have not taught in a very long time, which is Calc 2. Granted, I have been teaching differential equations a lot, so I have like the backfilled knowledge of how to teach this class. My notes are extremely messed up because at one point I was I was flipping through the notes and doing some stuff on the board, and then I looked down at my notes and I look at the board and I look down at my notes and I look at the board and I said, "Oh no, you can't do that." So it was an entire problem that I had to scrap. The next day, I had two formal complaints waiting in my mailbox. I'm like, "Are you kidding me?" But it was just because I was new to that particular section, and the students who had done it were kind of picky. They wanted like the best. They wanted the absolute best teacher who was there, and I'm like, look, I'm who you got. The class is 7 to 10 p.m. What do you want? But no, I didn't. I never addressed this obviously with the class or with them apart from just doing better with my notes. And then the fun part was the next semester I did the same thing because I screwed up and didn't change what section or change the example that I was doing. I caught it earlier. I didn't get to the dead end first. I got about halfway through it and I went, nope, nope, and I scratched it out and I take out my pen and just start drawing in my notebook, and they're like, "What are you doing?" I'm like, "Yeah, this example doesn't work." So it's a good example of how to fail. uh, but yeah, so I'm teaching one section of Calc 2 next semester, which again should be okay. I should be fine. And then I'm teaching two sections of our like math for liberal arts people class, which I'm hoping to bring in a lot of historical connections, which I do anyway for my pre-calculus honors class, and kind of formalize some of the like fun stuff and games that I talk about in the honors seminar. So start doing like I have to do a section on probability using cards and stuff like that. Oh, sure. It's probably going to get me horribly stuck or something like that, but go for it. So I've never actually taught that one in my, almost 15 years of teaching at this place. I've never taught this class. And the guy who had been teaching it for years left. And then we've had a coordinator for the last 2 years who has been, shifting stuff and changing things. And I'm just kind of like, I don't know how this is going to go because, these students are definitely not interested in mathematics. And I have to make it cool and interesting and fun. That was the other thing, was that my dean wanted me to teach statistics, and I was like, yeah, give me about a year, I might be able to figure it out. So given a number n, find out how many ways it could be written as the sum of three oh, no, just two consecutive. Wait. Yeah, yeah, okay. Two consecutive numbers. two or more, okay. Howlin' Ben, good evening. How's it going? So, Ben, good evening. My name is Obi-Wan Pez. I am a math streamer, and I do gaming occasionally, although last week on spring break it was a lot more than occasionally. It was like 4 days. So I do math streams on every Wednesday night at 9 p.m. Eastern or 6 p.m. Pacific. Um, and oh man, I gotta cut my hair. It's getting ridiculous. Absolutely. Is there any particular section you would like to talk about? True. Generally speaking. Yeah, so if we're looking at. I'll come back to that. So if we're looking at like the most basic definition of derivatives, what we're doing here is we're saying that, for instance, this is the Isaac Newton sort of thing. Um, he didn't do it particularly well, but it's fine. So what Newton did was he said, all right, let's take 2 points that are on a graph. And then I'm going to I'm going to connect these using a straight line. Now this is not a derivative. This is in fact what's called a secant line. So a secant line goes through a curve at two or more points, usually just two. We can call these by different names, so x1, x1, y1, and x2, y2, which you probably remember that going back to like algebra. Or, slightly more convenient, we could, sorry, we can call this one x and f of x. And this one over here could be called x plus h. So some distance, h, that's being added to the x value, comma, f at x plus h. Now, I do wish I had some animation software for this, but basically what's going to happen is we want to figure out what the slope of the curve is at this point here. So the slope of the curve here is going to be basically what is called a tangent line. or the slope of the tangent line. Okay, so the slope of the curve at this point is the slope of the tangent line through that point. So we want to figure out the slope of the tangent line through that particular point, x comma f at x. We're going to use a second point called x plus h by f of x plus h to get us a secant line that's actually going through two different points. Now you can clearly see right now this is not a very good approximation for that slope. It completely crosses it. It's just not even remotely close, right? But if we take this point and we shift this inward, we get this point here as our next point. Then what we end up getting is something that is, at the very least, closer to the green line. It's, again, not perfect, but it's at least closer. And then we continue this process, and we keep moving this blue point in further and further and further, and we start getting closer and closer and closer approximations for this particular slope. So what we're really doing here is we're taking h, and we're trying to shrink h down as much as possible. And since we're looking for the slope of this thing, the slope of the secant line is going to be given by just the same thing, y2 minus y1 divided by x2 minus x1 that we've been doing since Algebra 1. So in this particular case, y2 is going to be f of x plus h. y1 is going to be f at x divided by x2 is going to be x plus h minus x1 is x. Okay, this simplifies a little bit, not much, but f at x plus h minus f at x, all divided by h. All right, and in order to get the slope of the tangent line, which actually I should do this in green. In order to get the slope of the tangent line, what we have to do is take this, which is, again, the slope of the secant line, and say that x needs to be so small that it is close enough to 0 that it's going to make no difference. So how do we do that? Well, this is from section 1, right? We're going to take the limit as h approaches 0 of this thing. So want to take the slope of the tangent by taking the limit as h approaches 0 of the slope formula in function notation. And for different types of functions, this becomes really easy in order to figure out what the slope of that curve is going to be. So one of the ones that's always a favorite is if you're talking about all right, so 3x squared minus 4x minus 10, and we want to find the slope of the tangent line at, let's see, that's going to be in the positive direction. So 3, x equals 3. I'm going to be lazy about this. So technically 3, 5. All All right, so find the slope of the tangent line for this particular function at this point 3, 5. So what we do is we're going to say, if we don't know how to do derivatives yet, we go into this and we say, all right, now we've got to actually take the, we call this a difference quotient. So take the difference quotient of this particular function. And then this is going to allow us to figure out what the slope of the tangent line is, which is the derivative. So it is equivalent. This is, in fact, the way to calculate how to get the derivatives of parent functions. So for all parent functions, someday we'll be able to go through all of them. For this particular function, we can say that this is going to be, all right, f at x plus h is going to be 3 times x plus h, parentheses squared, minus 4 times x plus h, minus 10, minus parentheses, 3x squared minus 4x minus 10, still in parentheses, so don't do that yet. And then instead of writing this as all over h, I'm going to put this as 1 over h out front. And we're taking the limit as h approaches 0. Now, a naive approach to it. All right, see ya. For a second, I thought, Ben, you were leaving. I'm like, wait, what? I didn't finish. But hey, no problem if you had to anyway. All right, Hui Mate, see you later. Okay, anyway. So we're looking at this, and a naive approach would be to say, well, I'm just going to plug in 0 for h, and then that'd be it. So if we did that, what you get is here, this would end up being 3x squared minus 4x minus 10 minus 3x squared minus 4x minus 10. And so that would end up just subtracting the whole thing from itself. So you end up with a 0. And then you also end up with a 1 over 0. So you've got 0 divided by 0, which is, I don't know if you've heard the term before, but this is what's called an indeterminate form. So if you just plug in the limit without doing any work, you're going to get an indeterminate form. You don't actually know what's going to happen to this function, because if the 0 on top goes to 0 faster than the 0 on the bottom, then the whole fraction will eventually get smaller and go to 0. Or the 0 on the bottom could go to 0 faster than the one on the top, in which case the bottom gets small really quick, and when the bottom of a fraction gets small, the whole thing blows up, so it goes to infinity. Or they approach 0 at the same speed, at which point they approach a specific value somewhere in space. So there's 3 options, and you've got to figure out which one it is. So with this, unfortunately, just plugging in 0 isn't going to cut it. You end up with 0 over 0. So you can stop right there and be like, okay, that's not going to work. Okay, got to try something else. So here, what we actually do is we say, let's multiply all this stuff out. It's going to be a little bit of a pain, but it's okay. So we get the limit as h approaches 0 of 1 over h times the quantity. This is now going to be 3 times the quantity. X plus h squared is going to be x squared plus 2xh plus h squared minus 4x minus 4h minus 10 minus 3x squared plus 4x plus 10. One more. Okay, so then this is going to be the limit as h approaches 0 of 1 over h times the quantity. 3x squared plus 6xh plus 3h squared. Here, this is an interesting piece to note, is that we have a negative 4x here and a positive 4x here, and a negative 10 here and a positive 10 here. So with both of these terms there, this is going to become 0, and this is also going to become 0. So we got 0 terms that are going to be added, so we just drop them out. Then what's left now is a minus 4h minus 3x squared. Well, now we've got minus 3x squared here and here, or minus and plus, which also is 0. Then what's left is just this stuff in the middle. Only the terms that all have h in them. That's very important. So when you look at this, it says, hey, wait a minute. All these terms have h. And we've got this 1 over h that's sitting out front. That is super exciting because that means that we're going to have limit as h approaches 0 of 1 over h times, this is going to be 6xh plus 3h squared minus 4h, or if we factor out an h, actually let's even back this up one. We're going to factor out an h, and we're going to be left with 6x plus 3h minus 4. Then that means here h divided by h is going to be 1. Right? This is a number, h, and its multiplicative inverse, 1 over h. So when you multiply those two numbers together, by definition, it becomes 1. So that's gone now. And now we have just this stuff, 6x plus 3h minus 4. And interestingly enough, when you do the direct substitution now, take the limit as h approaches 0. When you plug in 0 in place of h, you get 6x plus 3 times 0 minus 4, but the rest of it is intact. Everything else is intact. This makes then 6x minus 4. This is the slope of the tangent line, which is equal to y prime or dy dx. Probably heard all of these terms before at some point. All right, this is the derivative function, which is going to tell you that at any point x, the slope of this parabola up here will follow this pattern here. Its slope, dy dx, will be equal to 6 times whatever your x value is, minus 4. Now, when Newton first did this, it was pretty awesome and pretty amazing. And he also came up with a series of notations that worked really well for him. He didn't care that nobody else could read it very well because it was for him, and who cares what everybody else thinks. So the way Newton would write this is usually y with a single dot above it. If he needed multiple derivatives after that, he just kept adding dots. And usually, he did not need any derivatives after the second derivative, so putting 2 dots above something was fine. Putting 3 dots was like, why would you do that? Didn't matter to him. And when physicists started using this and started putting 4 dots above stuff, because actually it is kind of useful, they started saying, well, this is really not good. We don't like this. As it turned out, Gottfried Wilhelm Leibniz, who was a German mathematician, had come up with a much better system of notation, which ended up being used by mathematicians specifically much more. Physicists still sometimes use the Newtonian notation, and mathematicians almost exclusively use the Leibniz notation. It also really helps when you take multiple derivatives on different variables, because then you can start saying, okay, I want to take the derivative of this function once with x and twice with y. And you can actually do that. Okay, so if we want to look at like parent functions and figure out what's going to happen with all these things. So when you start looking at just y equals x squared, y equals x cubed, y equals x to the fourth, these start getting a little tedious as you get through them. But at least at the very beginning, it's not that bad. So if we're looking at this in terms of what you get for all this stuff, this is going to be our x plus h squared minus x squared what we end up with here is that this is going to be 1 over h times, parentheses, x squared plus 2xh plus h squared minus x squared. Okay, the x squared terms go away, and we're left with this term, which has 1h, is going to divide nicely with this term, 1 over h. The h squared term, just like we had up above, is going to have a leftover h. And so it will have its limit approach 0, and then it'll be wiped out. So this here ends up being limit as h approaches 0. If you need one more step to it, that's fine. Just limit h approaches 0 of 2x plus h. Right, when you multiply in the 1 over h, then this is just going to be equal to 2x. All right, if you do it with x to the third, this becomes a little bit more tedious. It's fine. I also do a lot of work with Pascal triangles, and so this is pretty much exclusively a plus b raised to the nth power. So I'm kind of used to doing these. But so this ends up being x plus h cubed minus x cubed, which is going to be the limit as h approaches 0 of 1 over h times the quantity. This is now x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed. So first term's wiped out. The rest of these terms here have more h's than can be divided. So they are going to become 0, which means that this term here will be the leftover bit. Again, if you need to see it as written out, this is going to be the limit as h approaches 0 of 3x squared, multiply in the 1 over h, plus 3xh plus h squared. And that's going to just be 3x squared. So the derivative of x cubed is going to be 3x squared. All right, and similarly, the same thing's going to happen with x to the fourth. This is, again, a little bit more tedious. But again, if you know Pascal's triangle, it's not terrible. X plus h to the fourth minus x to the fourth. It's going to be limit h goes to 0 of 1 over h times x to the fourth plus 4 x to the third h plus 146 squared h squared 4xh cubed plus h to the fourth 1 h to the fourth minus x to the fourth. So again, first term goes away. The rest of the terms have more h's than are being divided, so they're all going to go to 0. And then you're left with 4x to the third times h divided by h. So just 4x to the third. And I'm not going to prove it because it takes a little bit more doing than I'm willing to necessarily do just right here. It's not terrible, but the point is that for any polynomial, you can have y equals x to the n, and it follows the same pattern. You end up with taking the limit as x goes to 0 of 1 over h times, this is x plus h to the n. That's supposed to be an n, not an h. Whatever. Minus x to the n. I said I wasn't going to prove it, didn't I? This is going to end up being x to the n plus. Here's the interesting thing about Pascal's triangle. The next row down, or as you read across on the nth row, this is going to be n times x to the n minus 1 h to the first plus this is actually going to be, this ends up being a what's called choose. So I'm not going to get into it, but there's going to be like some coefficient, which you don't need to know about right now, times x to the n minus 2 times h squared, and then all the rest of these have more h's. And eventually, we end up with a minus x to the n, just that one. Which then, x to the n here, minus x to the n there, subtract out, so that's 0. Then we're left with all this stuff. The 1 over h divides out the h from the first term, and the rest of them all have more h's. So again, this is the limit as h goes to 0 of n x to the n minus 1 plus a x to the n minus 2 times h to the first plus, and now all of these have more h. So when we take the limit, all this stuff is all going to be 0. So the derivative d dx of y, or d dx of x to the n, is always going to be n x to the n minus 1. Way off the... All right, hang on. Let's move that over there. There we go. I gotta watch where I'm going. All right, always, every single time. So this is what's known as the power rule. So every single polynomial term, you can always do this every single time. All right, so some of the other cool stuff that you can do with it. Hey, Soul Reaver, how's it going? Some of the other stuff you can do with it that's really cool is if you got like y equals c times any function you want. Doesn't matter. What's going to happen here is you're going to try to take the derivative of this thing. You take the limit as h approaches 0 of c times, c is a constant, so it doesn't get affected by the x plus h bit, c times f of x plus h minus c times f of x all over h. And now we can just factor out c. Limit h goes to 0 of c times that whole fraction, f of x plus h minus f of x over h. And c is not affected by the limit as h approaches 0. So it's a constant compared to this limit as well, or with respect to that limit. So the constant hops out. It's c times limit h approaches 0, f of x plus h minus f of x over h. And so this is just going to end up being c times, this is now the derivative of the function f of x. Oh no. Yeah, I would be interested to see what that is about. All right, so this is if we were taking d dx of c times f of x. So some function. All right, so c times f of x. Take the derivative of c times f of x, we end up with c times f prime of x. Or we just basically kick the constant out. So this is why when we were doing the other one up here, right, in green, when we were doing this thing in green, we had our 3 from the 3x squared, just kept getting carried all the way through, all the way to the end. and then our x, I'm still waving my pen around like you can see the cursor. All right. And if we look at the shortcut version, right, we basically are taking this 2 down and multiplying it out front by the 3 that's already there, and it becomes 2 times 3 is 6 times x to the first. We subtract 1 from the exponent, turns from 2 into 1. And then the next term down, the negative 4x, this is 4x to the first power. So we're looking at this and say, okay, we are going to take the constant negative 4. It gets multiplied, so it kicks out front. And then we take the derivative of x with respect to x, which is a power rule. So you can take this in, and we say that we take the derivative of x to the first. That's going to be 1. X to the 1 minus 1 is 0. So 1x to the 0 times the negative 4 that was already there, and we get that negative 4. The other interesting thing that happens is, and if you're actually like proving this, you have to do it. It's really boring sometimes, but somebody might think, for instance, that y equals x to the 0, if you took the derivative of this, then you'd end up with like 0 times x to the negative first. And it's sort of right, but it's also sort of wrong. The reason that it's wrong is that if you were to plug in, say, 0 as your constant, or 0 as your x value, right? This should work for all values. But if you plugged in 0 down here, that would cause a bit of a problem. And in fact, plugging in 0 here is a bit of a problem. Havel, not particularly, but if you want to give me a shot at it, we can try it out. It depends on what kind of question it is, because there are some resources that I have that are pretty decent. It's also been a while. Yeah, I was just talking with everybody else that I was offered the chance to teach stats this last year, and I was like, give me like a year, I'll figure it out. Okay, probability I can probably do. Yeah, no problem, Ben. If there are any other specific functions that you need, let me know real quick, and we can knock some of them out before we get any more requests. But yeah, calc is one of my specialties, so it's just kind of like I do all this stuff. So if you're doing these, if you're gonna like come across new functions, oftentimes it's very helpful to try and figure out the definition of derivative. Set theory I'm good with, so you can send that up, Havel. Yep. I hope I'm pronouncing your name right. Sorry. So last little thing about this, right, is that if you have y equals x to the 0, which really is just some constant c, then to take the derivative of this, you're saying that I want to take the function f of x plus h. Well, there is no x to plug in anything, so it's just c. So that's going to be y prime equals c minus c divided by h, and then we take the limit as h approaches 0. Well, this is just going to be 0. And technically, it's the limit as h goes to 0 of 0 over h. So it's just going to be 0. Right? It is 0 everywhere except at 0 itself. So the limit, right, as we're approaching stuff. All right, so Ben, do you need any other functions besides polynomials? If not, I'll be here in a week, so. No, just on Wednesdays for math. And Fridays for fun and games. But if you do have a question, like on a Friday stream, and it is urgent, I can interrupt the stream for a couple of minutes and throw up the whiteboard and do something real quick. That's not an issue. Yeah. I mean, people who join this channel probably understand it. Yeah. Unfortunately, I do have some other like actual work stuff to take care of. um, I don't really have a way to share it unless you are in. Um, so you can send it to nsimplexpachinko, my stream name, at gmail.com, and I will get that within a few minutes anyway. Let's see, which one is it? This one. Oh, boo. Haven't been in my inbox for such a long time. Come on. Not that one. Okay. Yep. However it's going to work for you, that's fine. Hate that. So it's the stream name, nsimplexpachinko, at gmail.com. I am hesitant to type it out in here just in case there's like bots or something. So, all right, I'm just gonna do something real quick here just in case. But you are welcome to continue, and I'll switch over once you get it typed out. So another interesting thing, Ben, is when you do something like y equals 2 to the x or y equals e to the x is usually the easier one to work with. When you're doing derivatives of e to the x, what you want to do is the same thing as we've been doing, right? So y prime is going to be equal to the limit as h goes to 0 of e to the x plus h minus e to the x divided by h. We can factor out, or we can break this up, make it e to the x times e to the h minus e to the x over h. So it's not a 1, it's a prime. It's more supposed to be like sort of a slanty apostrophe. Right, because if it's just y to the first, then it's the same as the original function. But clearly, these other ones are not the same as the originals, right? 2x is not the same as x squared. 3x squared is not the same as x cubed. So, Yeah, those aren't to the first. It's a slanty apostrophe. Oh, good times. I will get drawing that in just a second here. So more like that. So y prime is equal to limit as h approaches 0 of e to the x times e to the h minus 1 all over h. If you actually find the limit find the limit of e to the x is going to pop out. And then you're going to have a multiplier of limit h goes to 0 of e to the h minus 1 over h. As it turns out, there's a special limit for this. This is equal to 1. And so y prime for the original function y equals e to the x is e to the x. It is absolutely insane. So we can maybe talk about that some other time. It's one of the most handy, simple, and pretty awesome derivatives that you can find for all that. All right, let's do the stats. All right, so you got IBM, AT&T, and GE. You have the potential to own stock in just one, or two, or all three, and just put them in overlapping areas. It doesn't really matter which one is which. So, oops, not AT&A, AT&T, GE, IBM. All right, 50 owned shares in IBM. Right, so that is the total number of people who are in the IBM circle entirely, right? So 50 total, 40 in AT&T total, and 45 in GE total. So that is the entire circle. 20 own shares in both IBM and GE. 5 own shares, here we go. 5 own shares in all three. Okay. All right, 20 own shares in both IBM and GE. 20. 15 own shares in AT&T and GE. 15. 20 own shares in both IBM and AT&T. Now I'm wondering, since I don't actually know, right, since I have not done this problem, literally, when it says 20 own shares in both IBM and GE, is that double counting? So are we talking that this is what they mean? Or do they mean exclusively? Are we only talking about the people who own shares in just IBM and GE and not AT&T? So you have to be careful about this. So I'm inclined to believe that it is the intersection of both of these things. Yeah. I'm inclined to believe that this 20 is also including the 5 for all three. Well, we can try, right? So if there are 100 investors in total, this is also another way of. So if there are 100 investors in total, right, they say 50 own shares in IBM. That is everybody for all IBM. So because you just look at the total, right, it's 50 plus 40 plus 45 is already over 100. So they've got to be including, they've got to be talking about this inclusively rather than exclusively. Meaning that the 50 from IBM is going to be all of the circles together for IBM. Which is why I'm inclined to believe that anywhere that they say they own shares in both of these, it also includes the all three. So let's just speculatively try this out as it is. So if we've got 20 between IBM and GE, and if, right? So again, speculatively, if we're including the 5 here, then that means that we're going to have a total of 15 just for IBM GE and not all three. Similarly, this means that we're going to have another 5 plus this gets us 15, so that's going to be 10 here. This 20 is going to be another 15 and 5 here. Which then should mean this is 15 and 15 is 30, 5 is 35, and if the total for all IBM is now 50, we'll find out real quick if I'm right. All right, so this should be 15 if, again, 15, 15, 15, and 5 are going to add up to 50 for IBM. For GE, we've got the similar numbers here. So 15, this is another 15, and it's going to get us 45, so this total is going to be another 15. Over here, same thing. If this circle is 40, then we've got 15, and 15 is 30, plus 10 will be 40. Now, if we add up all these numbers, they should be 100. If we're not up to 100, then we got problems. Also, I would like to try it the other way just in case. So, yeah, 15, 15, 15, and 15 is going to be 60, 70, 80, 5. So either, well, that's interesting. So it never actually said anything about, like, nobody owning any of these. It could be just completely different. Oh, yeah, there you go. Did not have, how many investors did not have shares in any of these three companies? So if this is what we're doing, again, 15, 15, 15, 15 is 60, 75, 85 from 100 is going to leave you 15 outside. Okay. Now let's try it the other way and see if this is going to work. Because this is also another way to do it. Is try it a different way and see if it's completely wrong. So IBM, AT&T, GE. We said the total here was 45, total here was 40, and the total here was 50. We said the total in the middle is 5 that definitely have stock in all three companies. Okay, the intersections are 20, and again, did it not work? 20, 15, 20. Okay, so let's try it. If the intersections that we put on the outside before, just as like placeholders, that counted for both of these sections, the intersection of the two things, were instead just the exclusively including the exclusively intersecting parts of just IBM and AT&T and not all three. Then we put them in as 20, 15 here. This means that if we have 40 for AT&T total, this means we have 20, 25 plus 15 is 40, which means that nobody owns just AT&T. If we do the same for this one, this says that we have 25 plus 15 is 40 again, which means that GE is only going to have 5 people who own only GE stock and not any of the others. IBM, same deal, 40, 20 and 20 is 40, plus 5 is 45, so we have 5 that are now going to be just IBM and none of the others. Which means when you add them all up, we've got 20, 40, 50, 55, 60, 70. Which means that on the outside of everything is going to be 30 for none. So technically, this works either way. However, based on the way the question is worded, I would probably argue that this is the correct formulation. That because they said 20 own shares in both IBM and GE and said nothing about AT&T, that they were talking about both the centerpiece and the other one here. So that's an interesting thing. I would probably bring that up to your teacher and say, there are 2 different ways to solve this depending on how you read it. They may be suitably impressed. So the only reason that I say that it probably should include both is because when you say 5 own shares in all 3, we're also looking at the thing up top which says, for instance, 50 own shares in IBM, period. So that meant that it included the people who only went for IBM, the people who went for both IBM and AT&T, the people who went for all 3, and the people who went for IBM and GE. So again, like I said, if it depends on how you look at it. So if you're saying that when I say people owned IBM and GE, there were 20 of them, I could put that here to say that the people who owned both IBM and GE belong to both of these groups. The people who only owned IBM and GE, and the people who owned all 3. So the question is, which way is the book / your professor / whatever thinking about this? So if the answer ends up being that it includes the intersection of IBM and GE is the entire intersection of IBM and GE, this is what we get. If the intersection between IBM and GE that they're talking about, the 20, is just the exclusive intersection between IBM and GE, and it excludes the people who also have AT&T, then this is what you get. So there are two different ways to look at it, depending on where you draw the lines. So is your 20 who own both IBM and GE going to be here, this red segment, which is again the entire intersection of IBM and GE? Or is it the exclusive intersection between only IBM and GE? So again, like I said, it depends. If if this is Pearson, you can probably put him in on one of them, see if you get it right, and then do the other one if you don't. Because I know Pearson. Oh, I'm sorry. Yeah, a couple of my other people have similar problems due to the fact that my stream setting is like 720 only, and I didn't choose that, at least not that I know of. I did try to make sure that it would just be like automatic for anybody who wanted it, but maybe I can't do that unless I'm an affiliate, in which case that's not happening. Yeah, I've only got 720 as the option. That's too bad. Yep, I gotcha. So the second one here, can't see that. The second one here is if you're saying that the intersection that they're talking about, that IBM and GE, the people who own both IBM and GE stock, make up 20 people. And you assume that it is exclusively those who own only IBM and GE stock. Then this intersection here, is where your 20 are going to go. If, on the other hand, you think that it should go the other way, in which case, and like I said, I think this is the way they're going with this. If, on the other hand, you're saying that the 20 who own both IBM and GE could also include the people who own all three, then what we have is this segment here, which is the entire intersection between the companies IBM and GE. So people who own stock in both IBM and GE, whether or not they own stock in AT&T as well. Yeah. So that's why I said I think that this one is more likely. But you could also bring that up to your instructor and say, like, you could do it this other way if you read it differently, where like it doesn't explicitly say that we're only including or that we are also including the all three, and the numbers work out so that it is at least doable. It seems less likely, but the numbers are doable for number 2 over there. Nope, other way. The one that's further over. That way. The one that's like right here, I think again is more likely. All right. Anything else on that one? Yeah, sure. Either either DM or send it to that. Um, yeah, the email address. That's also true. Yes. Depending on the language that they use and the language that is included, it would definitely tip their hand as far as which one they're doing. All right. So, good evening to Rawiro. I haven't seen you around, so welcome. And to all of the bots who are here, welcome. Hope you're getting good information. I mean, all right, just 1 second here. What happened there? All right, so yeah, Ben, I can help you. All right, so 60 are in a club. That's your C there. 35 and 15 is 50 plus 10. Yeah. 40, play a sport. Uh-huh. 30 have a job. 20 are in a club and play a sport. 20. Yep. 10 are in a club and have a job. Yep. So that's all corroborating it. Yep. So like you said, you are including the people who belong to all three into the group of those who are only doing Yeah, no, I got you. Um, yeah, so it is in fact based on the one that you gave me. It is very much like this that one right there. So yeah, we are including anytime that it says we're including the people who are in both of these two groups, it is all of the people who are in these two groups, including both parts of the intersection, including the center, which contains the set of all three. So yeah. Yep. Yeah, the group that was outside of everything entirely. Yep, because the all the inside stuff adds up to 85. All right. Ben, where are you going to where do you want to send those? All right, if anybody has anything else, we can talk about it. I mean, like, I'll go practically the entire night, but that's not what I really should be doing. Okay, email. Yeah, Soul Reaver, if you want to send that to me, I'll take a look at it. Okay, that's fun. So, what your teacher is doing for that one is a thing which is called the chain rule, which is always so much fun. So, what this is really doing, let me put this up here. Integral x squared plus 2x over plus 1 squared dx. Okay, I'll come back. All right, so what we're talking about with the chain rule is that anytime that you take the derivative of a series of nested functions, so if we did like, yeah, I mean, we can just go with something similar but legally distinct from the one that you're doing. So if we want to do like ln squared of 3 tangent of, gosh, I don't know, what other interesting functions could we do? 2 to the x. This might be insane. We'll see how it goes. So if we wanted to do find the derivative of this thing, then basically what we're doing is we're looking at what kinds of functions do we have here that are nested inside of each other. Or, if you remember your pre-calculus, what kinds of functions do we have that are composed with one another? So if you remember your function composition, great. If you don't remember your function composition, well, you're going to be okay, but it's gonna hurt a little bit. So what we've got on the very outside of all of this is a natural log that's being squared. So really, at its most fundamental layer, a of x is going to be x squared. B of x is the next function in, right? The function that's being squared is a natural log. So b of x is the natural log of x. C of x is the function that is immediately inside the natural log, which is 3 times something, right? 3x. We could do that. You don't have to quite go this slow. You can speed it up if you want to. It's not a big deal. D of x is going to be, go inside one more, we've got a tangent of x. And E of x is going to be 2 to the x. Now, at its heart, what this is the function a of b of c of d of e of x. 1, 2, 3, 4, 5, 4, 3, 2, 1, 0. Cool. All right, so what we're doing here is we're going to look at this and say, well, this is kind of a large function, and it's kind of gross, but it's doable. All right, now what we're going to do is say that e of x is still going to be 2 to the x, right? This is at the deepest level, it's still 2 to the x. Here, the tangent of x can be rewritten now as the tangent of e. We're just going to use the function names as the variables that we're going to use here. So this may be interesting. It may be crazy. We'll see how it goes. C of x is going to now be 3 times d, right? This function that was here. Natural log of x is going to be the natural log of capital C. And x squared is going to be b squared. Now, what's going to happen with all this stuff is that we want to take, this is where you might hate me, it's okay. Usually my students do, it's fine. What we want to do here is take the derivative with respect to x of y, which is the derivative with respect to x of all this stuff. I'm just going to label it as A. So we want to take the derivative with respect to x of A as it fits as this whole long string of stuff. Now, we can take the derivative with respect to A. Nope, sorry. We could take the derivative of A with respect to x. However, that's only going to get us this far. I'm still pointing with my cursor, sorry. It's only going to get us this far. It's only going to get us to the x squared term. So it's not really going to get us to all this other natural log 3x, all that other stuff. So what we're going to do is say that this is not going to help. What's going to help is if we break the derivative of A with respect to x as instead the derivative of A with respect to B times the derivative of B with respect to x. So essentially what we've done is we've introduced a dB/dB and then shifted where our variables are going to be used. So this is now going to be dA/dB times dB/dx is also not particularly helpful because now we have a natural log of c in there. So we're going to take this as then dB/dc, dc/dx. But then we don't have an x there either. It keeps going. This could be dc/dd times dd/de times dE/dx. Now, e as a function is a function of x at its very core, at the very bottom here. So we're going to look at all of these individual things as this chain rule and say, okay, what's dA/dB? Well, dA/dB is taking the derivative of b squared with respect to b. So dB, replace it with a, which is b squared. Times ddc of replace b, which is the natural log of c. Times dd of c, which is 3d. Times dE of the function d, which is the tangent of e. Times, last one, ddx of 2 to the x. Okay, now all this, right, this is kind of insane, but it works. Just trust me on this, it works. All right, so this is going to be ddB of b squared is going to be 2b. And that's it. Technically, there's a dB/dB at the end, but dB/dB is 1. We discussed this a bit earlier. Times, this is going to be Havel. I might have screwed up, so it's perfectly possible. So in terms of calculus here, ddc of natural log of c is going to be 1 over c. Times ddd of 3d is just going to be 3. Times dDE of tangent of e is the secant squared of e. Times d dx of 2 to the x is going to be 2 to the x times the natural log of 2. Now, we have to very carefully go all the way back through this and plug stuff in. So, let's take all the constants out front first. So this is going to be 2 times 3 times natural log of 2, and we'll bring the 2 to the x out there as well, just to get it out of the way. So this is going to be a 6 natural log of 2 times 2 to the x times b is natural log of c. C is 3 times d. I mean, you could take a bunch of steps to do this too, just so it's not completely overwhelming and insane. I might be going a little overboard on this, and apologies. 3 times, you know what, we can do this, right? So natural log of c. C is, so we take this out, and we put in its place 3d. D is tangent of e, and e is 2 to the x. So we can back this up now as the natural log of 3 tangent of 2 to the x. And I'll collapse that now. 3 tangent 2 to the x. Now, it's also worth noting that this is basically the same thing as what we had at the top to begin with, and that is intentional. If you remember when we were doing like just when we were doing the derivative of b squared, right? This is 2 times b. Should do a prime or y prime. That is a prime is going to be 2b. Well, that's also the same b that we started with. So again, that's natural log of c, which then plugs in all this stuff. So, okay, then we get 1 over c. So times 1 over c is again 3 times d. D is the tangent of e, and e is 2 to the x. So all of this again kind of telescopes back up. So it's 1 over 3 tangent of 2 to the x. We'll get rid of that, move it over a little bit. So 1 over that thing. Then we get the secant squared of e. So, oh man. No, okay, I'm in the way. Yeah, there we go. All right, close enough. So we come down here. This is all multiplied by the secant squared of, again, e, which is just 2 to the x. And then that is going to be it. Okay, maybe I didn't need to go through all that dramatics there. It's fine. It's fine. So our y prime then is going to be this whole chain rule of all of this stuff. So it's going to be 6 natural log 2 times 2 to the x times the natural log of 3 tangent of 2 to the x, all divided by, and actually might as well just multiply, secant squared of 2 to the x, all divided by 3 tangent of 2 to the x. Okay, so this is what we've got. You could potentially, kind of gross here, but you could combine natural log terms. So you have multiplication between two natural logs. So that's going to become the 6 natural log 2 could become the exponent of the 3 tangent of 2 to the x. I don't know why you'd want to do that, but you could. You could also then look at the secant squared divided by the tangent, both of which have an angle of 2 to the x. So you could, in this particular case, also then look at this in terms of, do we have anything that can cancel out? Divide, both top and bottom. The secant squared is going to come down as a cosine squared, and the tangent will have one cosine in its denominator, which will then divide out this one, so it's a sine cosine. In addition, we also have a 3 here and a 6 here, which can divide out. So again, if we felt like it, I don't know why you maybe even would want to, but this could be 2 natural log 2 times 2 to the x times natural log of 3 tangent of 2 to the x. Again, secant squared can come down and become a cosine squared, and this has a division of a cosine, so sine of 2 to the x times a cosine of 2 to the x. So when you're doing chain rule, really the important thing is that every step that you're going through, you're checking to make sure that you're taking the derivative of the outer function, and then you set that aside, and you take the derivative of the stuff that's inside the function. And then you take the derivative of that function, set that aside, and take the derivative of anything that was inside that function. And just keep repeating this process as we go through. Again, this was a little bit insane and large, and you didn't have to do this. That may be me talking to myself. But at any rate, it's fun, asterisk, to kind of challenge ourselves with these sorts of problems, which on the face of them seem very difficult and very hard, which once you start applying the rules and you get used to applying the rules, they become almost trivial, where it's super easy to go through it and be able to complete anything you want. So, Hevel, let me know what happened here. What did I do that was different? Apologies for the throwing us around all over the place. So you got 50 in IBM, 20 of whom have both IBM and AT&T. So the 5 in the middle includes part of this 20 group, which means that 15 have to be just IBM and AT&T, none else. So that's your 15 and 5 make 20. Same with IBM and GE, 15 on the outside, 5 here. 15 for both AT&T and GE, which means you got 10 and 5. Just AT&T was 40, so 15, well, there were 20 between IBM and AT&T, and then that leaves 20, 10 of whom were between AT&T and GE. Make sure you're not double counting. that might also happen. Yeah, so if there were 15 between here and here, and 20 between here and here, keep in mind we have this 5 which is overlapping both groups, so you have to be careful with that. So 20 leaves another 20 for these two groups. We know 10 was here, so 10 has to be in AT&T alone. Same with going across here. We've got 15 and 5 is 20, plus 10 is 30. GE was supposed to be 45 total, so we're 15 shy. That goes in GE only. IBM, 15 is 30, plus 5 is 35. Out of a 50 total for IBM, means 15 is remaining. And then once you add up all of them individually, you end up getting 15 spare. So I'd be interested to know what numbers you got. So Ben, let's do a couple more easier ones that are going to be something similar to what you got there. So if we say we want the, let's say, secant of 2x minus 1 to the fourth. Actually, we didn't do product rule yet, so we'll keep it like that. So if this is your y, so y equals the secant of 2x minus 1 parentheses to the fourth power, and you want to take the derivative of this thing. So we're going to take the derivative of the outside function first. So the derivative of the secant function is going to be a secant tangent. In this particular case, essentially what we're doing is we're just saying that all this stuff is going to be a u. So d du of the secant of u is going to be secant of u times the tangent of u. How about a u instead of an x? Or d dx of the secant of u is going to be equal to the secant of u times the tangent of u times du dx, the derivative of u, the stuff on the inside, with respect to x. This is really how I would probably want my students to think of it. You got an embedded function u inside of the secant function. So the derivative of the secant function with respect to anything for that matter is going to be the secant of that same thing times the tangent of that same thing. Then you have to worry about what derivative are we taking and what's the stuff on the inside. So then we need to take the derivative of the stuff on the inside with respect to the variable we had outside. So this is going to be the secant of parentheses 2x minus 1 to the fourth times the tangent of the same. So now we need to take the derivative, so this is multiplied by d dx of 2x minus 1 raised to the fourth power. So when we take d dx of this stuff here, we can let let this inside stuff, 2x minus 1, just be like v. So this is going to be ddx of v to the 4th power is going to be 4v cubed times dv dx. Which is then going to be secant of 2x minus 1 to the 4th times the tangent of 2x minus 1 to the 4th times 4 times 2x minus 1 to the 3rd times, and now this is ddx of 2x minus 1. Well, 2x minus 1 is now a polynomial, so this makes it nice and easy. Take the derivative of 2x, you get 2. Take the derivative of negative 1, you get 0. So y prime is going to be equal to the secant of 2x minus 1 to the 4th times tangent 2x minus 1 to the 4th times this 4 and the 2 that we're going to get from this. It's just 2. So this is going to be 8 parentheses 2x minus 1 to the 3rd. So that goes back to this layer, and all that goes back to that layer. All right. Anybody have any other questions? I think it's getting late. So I am probably going to get off for the night and send y'all over to somebody. So I'd like to see what category, like what else do we have on categories here? Yeah, no problem. So I'm thinking the person I usually send people to is Jason Charles Miller, who is a really awesome musician, former frontman of Godhead, and has been doing some work with people from Geek and Sundry for several years. He's a really awesome dude. Looks like a country music star, kind of more of a rocker, and does a lot of music stuff. So tonight is Whatever You Want Wednesdays, and the he does it for donations, but you don't have to do anything. You just listen for free because he has a queue that's very long. So don't worry about spending money on that. That's anyway. And very often his people will gift so many subs that you will probably end up getting a subscription just by coming. So I think I'm probably gonna raid Jason Charles Miller because he's a great guy. So I will be back on Friday for a game stream. I'm probably going to stick with Astroneer this week and do a regular regular sized stream, probably not a dual stream where I do two different games. Also been playing Control. I might take a week off from that or whatever because I got some other work that needs to be done. But and sleep. So whatever. Um, and then next Wednesday, I will be back for another math stream. Feel free to send anything to that email address, nsimplexpachinko@gmail.com, and I will be sure to check it a couple of times in the next week. And I hope you all have a great weekend. I hope you all have a great week. And I hope to see you again, because this is great. Having extra people here, being able to bounce ideas off of, anything like that. And if you have any, methods in which your teacher has taught something that you don't understand, you can also send those, and I will try to decode them for you and help you understand how they all work. So, this is Obi-Wan Pez for N Simplex Pachinko. I will see you all, hopefully, very soon.